So our bitstream generation is successful. Now we'll go ahead and we will be first exporting our hardware, okay, including a bitstream. That is the first step. And the second step is to launch an SDK. So whatever C application that we'll be developing for this example is eligible for our previous video also, when you want to interface an external hardware, okay, with an UART peripheral using EMIO, okay. So let us just go ahead and try to first create a new application project, right? So we'll go to File, New Application Project. We'll just be naming this as UART EMIO, okay, and then we'll hit Next and click on the Hello World template and we'll hit Finish, right? So here also Hello World template is eligible because anyways we are utilizing UART1 for debugging purpose, right? Now once you go to system.mss, we'll be finding a recommended driver. Now we have two instances of UART Lite and the recommended driver for us is UART Lite, right? So we'll go to helloworld.c, right? So let us proceed with development of an application, right? So we'll include two header files over here. First one is where we find all the hardware related information, that is xparameter.h, okay, and the next one is the driver file for the IP that we have included, right, in our hardware design, and that is xuartlite.h, right? These are the two things that we'll be doing. Now if you go to UART Lite, you could find out that we again required a two structure for initialization of UART, right? So you have UART Lite config and you have UART Lite, right? So again we'll be following the same process as we've been doing from the beginning. So we'll copy UART Lite, okay, we'll be adding it over here. We'll just be naming this as UART, and again for UART Lite config we will be declaring as a pointer, right? So we'll just go ahead and we'll add this, okay, this will be UART config and this should be a pointer, right? So we'll just be adding an asterisk over here. Now this should be for both the IP instances that we have created, right? So for first instance we'll just be naming this as UART 0, and for the second instance we will just be naming this as UART 1 and UART config 1, right? Let's just go ahead and create an independent function, okay, which could be used to initialize our UART peripheral, okay. So we already know the process, so let it just declare two variable in status 0, okay, and status 1. So this will be holding the value written by CFG initialize for both the instances of an IP, right? So we need to look for a lookup config, and we do find a lookup config where we need to pass a device ID, right? We'll just go ahead, and then to find out the device ID we just need to go to xparameter.h, right? So if you go ahead and look for an UART, right, so you could find out the data related to both the UART instances, right? So this will be the device ID for UART Lite 0. So we'll just copy it and we'll add it over here, right? So this returns a config structure and that will be connecting to UART config 0 since this belongs to UART 0, right? The same thing that we'll be doing with UART 1 also, right? So we'll just copy this, we'll be adding it over here. We'll just be replacing this 0 with 1, and the device ID for the device 1 is this one, right? So we'll just copy it, we'll go ahead and we'll add it over here, right? So this is the first step where we look up for a device ID and return the config structure. The second step is to utilize. Now we will look for CFG initialize, right? Again it requires three arguments: the instance structure, the config structure, and the effective address, right? So we'll go ahead, and then first is a UART instance, right? So for first UART Lite IP we'll just be adding UART 0. The config structure for UART 0 is UART config 0, right? And the last one is the base address. So UART config 0 structure do consist of the base address, right? So if you just look for the base address inside this structure, you could find out the base address, right? So we'll just be adding it over here, right? The similar thing we do need to do for our second instance of an UART light IP, right? And this returns the value which we want to store in a status 0, right? Now we'll just copy this and we'll be adding the same thing for our UART1, right? This will be UART1, this will be UART1, and this will again be an UART1, right? Now we just need to verify whether both status 0 and status 1 is equals to access to success, and if that is the case, we basically say that our initialization is successful, right? So if status 0 and status 1, if both are equals to access to success, okay, so if that is the case, then we could say that still printf, okay, so device initialization is successful, that is UART 0 and UART 1 init successful, right? Else what we could do is printf, here we will just be mentioning device init and then fail, right? So this completes the step 1, right? Now we require to use init platform and cleanup platform, because this will be used to initialize our UART1 which is connected to a processing system, and that we are utilizing for a debug purpose, right? And this all thing is related to the 2 UART light IP that we have added, right? So just after an init platform, we'll just be calling UART init, right? So let us just go ahead and try to perform an execution of this code. So that will give us an idea whether device initialization is successful or not, right? So we'll not be adding any other still printf to send an hello world, okay, because we just need to verify whether device initialization is successful, and then we'll start building up our application, right? So first we need to program our FPGA. So once programming is completed, we go to an SDK terminal. We'll be connecting to COM4, okay, and at the rate of 115k. So let it just go ahead and try to perform run as launch on hardware, right? So here our agenda is just to verify whether device initialization is successful, right? Now you could see we have a message that UART initialization is successful for both the instances of a UART, right? Now we could explore and develop an application. So what we will do here is, since we already know few APIs, okay, when we are working with an UART PS, here let us just try to send the simple data and try to receive it, right? So that will help us to understand whether both of them are working in a loopback mode, right? So let us just go to an UART light, okay. Here we do have a function, okay, that is used to send the data. So let us just copy it, and this required a 3 argument. First one is an UART instance structure, then the data buffer, and the number of byte that we want to send, okay. So let us assume we want to send a single byte, right? So U8, which is the data type our UART could send, okay, and then this will be DS, okay, that basically means we want to send the data. And we also required one same data type variable that could be used to receive the data, okay, from RxV4 of an other UART instance. So we'll just be naming this as DR, right? So let us just keep this 8, okay, and let us just initialize this to a 0, okay. You could explore the same functionality with an array also, okay, that doesn't change much, right? So let us just go ahead and add a send. Now what we will assume is UART 0 is sending this data, okay, and then UART 1 is receiving. Then we will be sending the data from UART 1 and we'll be receiving in an UART 0, right? So let us just add an UART instance as UART 0, okay. The pointer for our data buffer is basically an address of DS, so ampersand and then DS, right? And then the number of bytes. So since we only have a single byte, we'll just be specifying 1, right? Now we'll be waiting for the data transmission to complete. Again, this is exactly similar to what we are doing in the previous case. So while UART 0 is sending a data, so here we just need to specify UART 0. We just will be waiting over here, and then we will be receiving the data. Now this pins of TX is connected to RX of our UART 1. So we just need to go ahead and find out the receive function, okay, and then we will just be receiving the data over here, right? So let me just add this function. Now the UART instance which will be receiving data is UART1, okay. The data buffer for us is dr. Again, since this is a pointer, we'll be utilizing an $dr, and the number of bytes that we want to receive is 1, right? So once we receive the data, what we're gonna do is we'll just be printing the data that we received, right? So zil printf, okay, here data received, okay, and this will be from UART1 instance, okay, and we'll just be printing the decimal value, and the data will be inside a dr, right? So just before calling a send API, we could just mention the message that data sent, okay, from UART0, and this will be ds, okay. So this could be helping us in comparison, right? And do not forget to add a new line character over here, right? So what we are doing is we are first mentioning the data that we are sending from UART0 interface, okay, then we are calling the send API, okay, mentioning all the important parameters that this function requires. We are waiting for transmission to complete, and then we are receiving that data utilizing a receive API, right? And we are again printing this. So let's just go ahead and try to execute this application, okay, whether we are getting what we are expecting out of it, right? We'll just be clicking on run option, okay. So this will relaunch our debug section, and now you could see that UART0 and UART1 and it's successful. So data send is correct, okay, and data received is 0. So let's just go ahead and try to find out. So we could just wait for entire process of reception is completed or not, right? So we could just wait for entire process of reception to complete, right? So we'll just be adding if, okay, let it just add one integer, okay, and then this will be count the bytes, okay, so the number of bytes that we have received. So this function returns the number of bytes that we received, right? So here we'll just be mentioning if count byte is not equals to 1, right? In that case, we will just be executing this code continuously. That is, we will be continuously waiting for a reception of a data, okay, and here we just will be mentioning count byte equals to, okay. So now what this will do is, with the addition of this code, this will allow us to wait till we receive the byte, okay, and then we'll be printing the data, right? So let me just go ahead and see whether code is working with this modification. So now you could see, okay, in the previous case, since our reception is not completed, okay, we able to see 0, but now once we add this logic, that is we are waiting till we completely receive the byte that we specify. Now here we are receiving a single byte, so the count that we mentioned is 1, okay, and now you could see UART0 and UART1 and it's successful, okay. So data send is 8 and data receive is 8, right? So we able to connect these two IPs, okay, such that the data from one of the UART IP could be received in other one, right? So without an hardware, this could be your strategy, because we have a multiple interface that are available on a Zynq processing system, and you may not always have an hardware for it. So you could just connect them in such a way that you send and receive with the same interface and then verify the data, right? So as we progress further, we will be exploring this concept with another interfaces also, so you get a fundamental understanding of how you could tackle a situation when you do not have an hardware, right?